Welcome, folks. We're looking at the first objective for Algebra 2 B. Here we're going to be talking about radical functions and rational exponents. We'll remind you what those mean in a minute. Here we go. Now, when I say I'm talking about radical equations or radical expressions, really what we're talking about here are roots. Okay, so as in square roots, third roots, fourth roots, stuff like that. And remember, the way we define the nth root is for real numbers a, b, and positive integer n. If I have this, the nth root of a equals b, well, that just means the same thing as b raised to the nth power is equal to a. Okay, so for example, I know that the square root of 9 is equal to 3. Now with square roots, we typically don't write the index here, but I could write this as a second root. Okay, the second root of 9 equals 3 because I know that 3 raised to the second power is just equal to 9. Okay, so really what our roots are giving us is the number that I have to raise to the certain power, okay, to get what we're taking the root of. Another example quick, I know that the third root of 8 is equal to 2 because 2 to the third power, in other words, 2 times 2 times 2, is equal to 8. And I can do the same thing with fourth roots, fifth roots, 10th roots. We'll keep it simple with 2, 3, and 4, but it's going to work the same way for any root. Now, a few things for you. We'd say that b is the nth root of a. In this case, okay, what is equal to is the nth root of a. And then also we'll use this word as well. N is the index. Okay, the index is what type of root we're taking. Again, with square roots, we usually don't write it here, but for a third root, I'd write the 3. For a fourth root, I'd write the 4 here, and so on. So let's go ahead and jump into some problems. One of the big things we're going to do as we go through this entire lesson is simplify radical expressions. Okay, so we want to take this big ugly mess here and simplify it down. Now, a radical expression, again, that's just an expression with some type of root in it. Here we have a third root. And I want to see if I can pull all my perfect cubes out of here. Okay, so let's go ahead and do that. First thing I want to do is deal with this 125. Now, I don't know all my perfect third roots off the top of my head, so let's factor tree this thing apart. If I take 125, I know it's divisible by 5, so I can rewrite that as 5 times 25. And if I need to use a calculator for that, feel free. 25 then I know is 5 times 5. Okay, so what I have here is I have 1, 2, 3, 4, 5s that make up that 125. So the way I'm going to rewrite that is I'm going to rewrite this as the third root of 5 to the third. And the reason I did to the third power is I know the third root and third power are going to cancel out. And then I want to do the same thing with my variables. Okay, x to the 9th, I can rewrite that as x to the third power. Okay, the way my exponents work is when I would raise exponents to exponents, I'll multiply them. 3 by 3 is 9. And again, I'm looking for factors of 3 just so that third root can cancel it out. Okay, y to the third, I'm just going to leave that as y to the third. And then z to the 6th, I'm going to rewrite that as z squared to the third. Again, because 2 times 3 will give me that 6. And again, I'm looking for things to the third power, so they'll cancel out. Okay, so here's a case where everything is going to work out nicely. You can think about this third root as canceling anything out to the third power. So I could rewrite that as just a 5. Okay, the third root's going to cancel out one of these two 3's. We'll do the one on the outside, so that would be x to the third. Third root's going to cancel out the third again for the y to the third. So we can write that as just a y. Now I could say y to the 1 if I wanted to, but not necessary. And the same thing with the z will cancel out to the third power, so we're left with the z squared. All right, I'm going to say that's my answer in simplest radical form here. Okay, we pulled out all the perfect cubes, all the perfect third power factors from this original expression. We'll get into later when we leave stuff on the inside when it doesn't work out perfectly, but I'd say that's my simplest radical form for this example here. All right, that's part A. There's a part B in your note packet as well. Why don't you go ahead and pause the video, work through that one, give that one a shot. I believe it's a square root, so you're looking for groups of 2's. And then once you're done with that, check your answer before you hit play again and move on with the video. Next thing we're going to take a look at is combining radical expressions, okay, through the product and quotient rules. In other words, multiplication and division. Product rules just says that if I have the nth root of a times the nth root of b, so the same type of roots of two numbers, I can just multiply those numbers together underneath that same root. Okay, so for example, if I have the third root of 2 times the third root of 5, that's just going to be equal to the third root of 2 times 5, which is a 10. Okay, so in that case, I can combine them because they have the same indexes here. They are the same type of roots. Another example, I guess, is when I couldn't combine. Let's say that I have the third root of 2 times, let's just say the square root of 5. Okay, in this case, I can't do anything different with this. This would just be equal to third root 2 square root 5. That's all the simpler I can make it. Since these don't have the same index here, I can't put them together. All right, then we basically have the same thing with division. If I have the nth root of a divided by the nth root of b, this just says I can take the nth root of a over b. So let's say we have square root of 6 divided by the square root of 2. Well, that's just going to turn into the square root of 6 divided by 2, 3. Again, since it's the same type of root, I can actually combine those. Let's go ahead and use the product and quotient rules in the next couple problems. Okay, what's the simplest form of each product? Here I've got one rational expression times another one. Okay, so what we'll do is, since these are both square roots here, the same type of index, I can combine these through multiplication. So the first thing I'm going to do is multiply whatever's on the outside. 5 times 2 is just a 10. All right, then times will have the square root of, same thing, 10 times 15 is going to be a 150. All right, then combining my variables, a to the third times a squared. Okay, remember when you're multiplying numbers with exponents together, you add the exponents. That's going to be a to the fifth power then. And then times, same thing with the b's, b to the third times just a b, or in other words, b to the 1. We'll add those together. That's going to be a b to the fourth. Okay, so multiply, and then we want to simplify. So now we're back to where we were with the last problem. Okay, I want to rewrite things in terms of squares, because again, this is a square root, so I'm looking for that second power to cancel out. First thing I'm going to do is deal with this 150. Let's factor tree it again. 150. Now I know that's even, so I can divide it by 2. That's going to be 2 times 75. 75 is divisible by 5. That's going to be a 5 times a 15. 15 is divisible by 5, which would be a 5 times a 3. Okay, what I'm looking for is I'm looking for groups of 2 numbers at a time, because again, my square root will cancel those out. So I can rewrite this as 10 square root of, let's say, 5 squared times the 2 times the 3. And then I want to do the same thing with the a and the b. All right, a to the fifth. That's not going to work out perfectly. We can't write 5 in terms of 2's, but what I can do is I can say that's a squared squared. Okay, because multiplying those exponents, that'll give me an a to the fourth. Okay, times an additional a to the 1. And then for the b to the fourth, we can rewrite that as b squared squared. And now I'm able to do my canceling. Anything that is square rooted, what we'll do is we'll pull to the outside. And anything that is not squared, sorry, not square rooted, but squared, we'll pull to the outside. Anything that's not squared, we'll leave on the inside. Okay, so what I'll have on the outside is a 10 and a 5. I'll just write that as 10 times 5 for now. And then what else will we have on the outside? Well, we'll have a squared, because that square root's going to cancel out this square here. And we'll also have a b squared, okay, for the squared piece that gets canceled here as well. And on the inside, we'll just have all the stuff that wasn't squared that won't cancel. We'll have a 2 times a 3 times an a. All right, so then simplest way I can write this expression then is 10 times 5 is just a 50, so multiply all the numbers together. A squared b squared, square root of 2 times 3 is 6, 6a. All right, I'm going to say that's my simplest form of this rational expression. Now, we probably did one additional step we don't need to show here for this one, but if it's helpful to show all your work to get the problem right, definitely do that. All right, but there's an example of multiplying and then simplifying. All right, same idea with problem 2. There is a part B, so once again, pause the video, work through that one, and then check your answer before you hit play and move on. Next, let's go ahead and take a look at a division problem. Okay, so what's the simplest form of the quotient? Rationalize the denominator. We'll talk about that when we get to it. Okay, so for this one, since I have a third root divided by a third root, I go ahead and just divide the two of these. I can write it as a third root of just these fractions divided. So let's go ahead and do that. 8 and 18 won't reduce perfectly, but I can pull out a 2 from both those numbers and rewrite that as 4 over 9. All right, x to the 5th divided by x to the first power, we could say. Remember, when you're dividing numbers with exponents, you subtract the exponents. 5 minus 1 is 4. So we'll call that an x to the 4th on top. And then there's just a y and a z to the 3rd, which we'll leave as is. There's nothing I can combine there. Okay? And then just like we did with the last set of problems, we want to simplify this. But before we do that, I want to take some steps to rationalize my denominator. In other words, I want to get all the perfect cubes. I actually want to get everything in the denominator out of the cube root. Okay, why would I want to do that? Well, it's just going to make it a little easier to work with. So let's go ahead and rewrite that denominator in a form that's going to be easier to rationalize. Numerator we'll leave as is. We'll deal with later, such as the x to the 4th canceling out. Denominator, I'm going to rewrite the 9 as a 3 squared. The y I'm going to call a y to the 1. And z, I'm going to write a z to the 3rd. Okay, because what I want to do here is I want to multiply top and bottom by factors that are going to turn everything on the bottom into a perfect cube. So for example, to make 3 squared to the 3rd, I need to multiply by 3 to the 1st power. Now if I do that on the bottom, I've also got to do it on the top, because then I really am just multiplying by a fancy way to write 1. Same thing with the y. I have y to the 1. I need y to the 3rd, so I'd have to multiply top and bottom by y squared. And then the z, that's already to the 3rd, so we're good with that. Okay, so I'm going to multiply top and bottom by the 3rd root of 3 to the 1 y squared. And that's going to give me then on top the 3rd root of, well, 4 times 3 is just a 12. X to the 4th times y squared is just x to the 4th y squared. Okay, over on the bottom, 3 to the 1 times 3 squared will be the 3rd root of 3 to the 3rd. Okay, y to the 1 times y squared would be y to the 3rd. And then again, we have that z to the 3rd tagging along. So we kind of run out of room here. Now the reason we did that is in the denominator, the 3rd root's going to cancel with all these 3rd powers. So what I'm left with then is just a 3yz. The numerator will rewrite so that we're able to simplify. Okay, so I'm going to write that as the third root of 12. We'll just leave as 12. Okay, a little scratch work on the side. 12 is equal to a 2 times 6, which is equal to 2 times 3. Now, there's no groups of 3's to pull out, so we can't simplify that any further. X to the fourth, though, we can write as x to the third times x to the 1. Okay, the third will come out, the 1 will stay in. Y squared we'll just leave as y squared. Okay, so the final simplest version of this we can rewrite as the numerator as just an x for the x to the third that'll cancel and come out front. And then just third root of 12, we're left with 1x and a y squared. All right, all over 3yz. Okay, I'm going to say that's my simplest form of this quotient here with the denominator rationalized. All right, so kind of the same thing we've been doing with simplifying. I guess the one new step here is just that rationalizing the denominator part. All right, part B is the same idea. Once again, take a minute, pause the video, work through that one, and get your answer checked before you move on. All right, next thing we're going to take a look at is adding and subtracting radical expressions. Okay, so for that, what we're going to need to talk about first is like radicals. I'm going to say like radicals are radical expressions that have the same index and the same radicand. Okay, so again, the index is the type of root we're looking at, and radicand, we haven't used that word yet. We'll just say that's what's underneath the root. And then my rules for adding and subtracting radical expressions, if I have like radicals, okay, same index, the n in both cases, and the same radicand, the same thing under the roots, the x, what I can do is I can just combine those two numbers here, okay, through addition, the numbers out front. Same thing with subtraction. If they are like radicals, I can just subtract the numbers out front. Okay, so for example, if I have, let's say, 2 square root 3 plus, let's say 1 square root 3, since those are both square roots of 3, all right, I can just count how many square root 3's I have. 2 plus 1 is 3. We can write that as 3 root 3. As another example, let's say I have 3, let's say third root of 5 plus 2 third root of 3. Okay, here I'm going to say I can't actually combine those since I have the same index. They're both third roots. All right, but one radicand is 5, the other one's 3. I can't actually put those together. This is actually as simple as I can make that. Okay, so let's go ahead and jump into some problems with addition and subtraction. Okay, simplify each expression. Now here what I'm looking at is all these roots are third roots, so we're good there. But I've got different radicands, different things under the roots in each case. So I can't combine these right away. What I can look to do though is simplify them first. So for example, let's go ahead and break down this 135. 135 is divisible by 5. It is a 5 and a 27. Okay, and 27 I know is a 3 times 9, which is a 3 times 3. Okay, so there is a perfect third root. So what I could do is I could rewrite that 135 as 3 third root 5. Okay, because that 3 had come out, the 5 would remain. Now I have a like radical with this 5. Let's go ahead and see if we can do the same thing with the 40. Okay, 40 is even, so I'll say that's a 2 times a 20. And 20 is 2 times a 10, and 10 is a 2 times a 5. Okay, so once again, there's a group of 3 2's that I can pull out. So we can say that's really minus, instead of third root 40, we could say it's minus a 2 third root 5. Okay, plus the third root 5. Okay, so look to simplify first, and these all did simplify down. Now what I can do is just count the numbers up front. Okay, 3 minus 2 is a 1, plus another 1 would be a 2, third root 5. When I combine these all and put them all together. Okay, so again, the idea there is simplify first, and then you can look to combine like radicals. Okay, once again for problem 4, pause the video, go ahead and give B a shot, and again, check your answer before we move on. Next thing we're going to take a look at is rational exponents. Okay, and what rational exponents are is just a way to rewrite a radical in terms of rational exponents, exponents with fractions in other words. Okay, and what this rule is telling me is that if I have a to the m over n, that's the same thing as the nth root of a to the m. Okay, or we could flip the order, we could say it's the mth power of the nth root of a. Okay, either way you write it here, what we have is the top of my fraction is the power we're raising things to. And then the bottom of my fraction, the denominator, is just the index, it's the type of root we have. Okay, we'd use this to simplify a lot of different types of expressions. We're not going to do too much with rational exponents in this kind of short review lesson here. Okay, but there's a lot of ways I could solve problems with them that I wouldn't be able to do without them. First thing we're going to do is just rewrite things in terms of rational exponents. Okay, so write the radical expression, the root expression in other words, in exponential form. Okay, so I'm just going to essentially work backwards through this rule here. Now, since I have a square root, okay, that index is just a 2. We don't have to write that, but we know that. So I can just rewrite this as x to a fraction power, where the power is the top of the fraction, the 3, and then the type of radical we're dealing with, the type of root we have, is just the bottom of the fraction. All right, that's it. That's all there is to it. We're just using this pattern here. Okay, we'll do some more with it in future problems. But for now, again, why don't you pause the video, take a minute, and work through part B before we move on. All right, the next thing we're going to do is utilize rational exponents to simplify problems. Okay, so problem 6, write each expression in simplest form. Now this whole expression of the fourth power, I'm going to say that's the same thing as the fourth root of 32 x to the 8th y to the 4th. Now that's something we already dealt with here. I could just simplify from here, but I'm going to say this is going to be a little bit simpler if we leave it in exponential form. We'll show you some shortcuts we can take. Okay, so if we think about this in dealing in terms of exponents, if I'm raising exponents to exponents, all I've got to do is raise everything to the fourth power here. Okay, now 32 to the fourth power, we'll just write as 32 to the fourth power for now. Okay, for the x to the 8th, raise the fourth power. Remember, the rule we're used for combining exponents raised to exponents is we'll multiply. So what this is 8 times 1/4. Okay, now if I think of this in terms of 8 over 1 times 1 over 4, that's just 8 divided by 4, which is a 2. So I can write that as x to the second power, x squared. And then we can do the same thing with the y to the 4th, raised to the 1/4 power. Okay, 4 over 4 just cancels, so we're left with there is just a y to the 1. All right, x squared y to the 1. So really what that did is that took care of all the simplifying for me using exponent rules. Now I am going to have to think in terms of radicals for this 32. So we could rewrite that as the fourth root of 32, all right, times the x squared times the y to the 1. Okay, on the outside of the root right now. And we can break 32 down. I know that's a 2 times a 16, which is 2 times an 8, which is 2 times a 4, which is 2 times a 2. Now with that fourth root, I'm looking for groups of 1, 2, 3, 4 2's together. Okay, so that's a perfect, what's the word I'm looking for? Quartic I can pull out. Okay, number raised to the fourth power with a 2 left on the inside. So for my final answer, what I could write this as is a 2 for the 2 I'm pulling out of the fourth root, x squared y. And then we'll have that 2 remaining on the inside. Okay, fourth root of 2. Okay, that's going to be the simplest way I can write this expression. Once again, could I do that all in terms of roots? Yeah, but I'd say kind of dealing with the exponents here, it's easier to use our exponent rules to take care of those right away. All right, once again with part B, pause the video, give that a shot, run through it, and then check your answer before we move on. All right, next thing we're going to do is looking at solving radical equations. Okay, we'll take a look at a few different types of questions. Okay, we'll start off with just square root equations. Now that's just an equation with a square root in it. Now the trick for solving a square root or really any type of radical equation is going to be to just get the radical by itself, isolate the radical, we'd say. So the first step I do for this equation is I'm going to subtract 3 on both sides. That's going to leave me with the square root of 2x minus 3 is equal to a 5 on the right. And the reason I did that is just like we've used square roots to cancel out things squared, we can just square both sides to cancel out that square root. Now I can't do that right away with this plus 3. I've got to get that root by itself. But then what's going to happen, you really won't usually show this step, but the root and the square cancel out. What I'm left with then on the left side is just a 2x minus 3. And on the right side, 5 squared is just 25. So what I have then is a simpler linear equation that we can go ahead and just solve for the x. Okay, add 3 to both sides to cancel out the minus 3. That's going to give me that 2x is equal to 28. And finally, divide both sides by 2. That's going to give me that x is equal to a 14 here. All right, so x equals 14. If I plug a 14 into the left side of the equation, we'll get the same answer as the right side. We'll get into checking for extraneous solutions in a couple minutes here when we get into some other problems. But for now, we'll just say, there we go, that's the answer. All right, same idea with part B. Once again, go ahead, pause the video, work through part B, check your answer before you move on. All right, let's take a look at problem 8. Here we're solving radical equations in general. Okay, so rather than just square roots, we'll look at other types of roots. Okay, here now this one is a radical equation. Right now it's written in exponential form. And we're going to look at 2 different ways we can solve it. The first way is going to be just to rewrite things in radical form. So we'll rewrite this as 3 times, we've got, since the 3 is on the bottom here, a third root of x plus 1. Numerator of that rational exponent is the power raising 2 squared is equal to 12. Now solving this guy, once again what we'll do is we'll isolate the radical. I've got to divide both sides by 3. That's going to give me the third root of the x plus 1 squared is equal to a 4. And then what I can do with the next step is get rid of the root. I'm going to raise both sides to the third power to cancel out that third root. That'll leave me with just a x plus 1 squared on the left. All right, is equal to a 4 to the third power is a 64. And then what I'll do is I'll just square root both sides of the equation to cancel out the squared. That'll leave me with a x plus 1 on the left is equal to, now when I'm square rooting, remember I have to include a plus or minus. We'll say plus or minus 8. So really here, 2 equations to solve. 2 linear equations though. That'll leave us with an x plus 1 is equal to a positive 8 and an x plus 1 is equal to a negative 8. I'm going to subtract 1 on both sides for both equations. I guess I'm kind of doing two things at once. Probably not a great habit to have. But I'll give us x equals 7 and x equals negative 9. Those will be my two solutions for this radical equation here. All right, that's one way you can work through it. Let's show you an alternative way that kind of utilizes rational exponents a little bit more. Okay, and you can decide which one you want to use come test time. So if I have the 3 times the x plus 1 to the 2/3 power equals 12. Let's go ahead and just leave this one in exponential form. So we can divide by 3 right away to cancel out that multiplication by 3. So then we have the x plus 1 to the 2/3 power is equal to 4 once again. And then to get rid of this exponent, what I'm going to do is I'm going to raise both sides to the reciprocal 3/2 power. Okay, because if I raise 2/3 of the 3/2, those will just cancel. That'll leave me with the x plus 1 is equal to, then we have 4 to the 3/2 power. Now here what I'm going to have to do is evaluate. Okay, so I could write that as the square root of 4 to the 3rd. And I guess the one trick with doing it this way is if I'm taking something to a half power, I am taking a square root, so I would need to include the plus or minus. Okay, I think that's a little clearer doing it this way with the roots. But anyway, we can solve. So x plus 1 is equal to plus or minus the square root of 4 to the 3rd, which is 64. Okay, so x plus 1 is equal to plus or minus the 8. And then once again, we have the two equations to solve. X plus 1 equals 8, and x plus 1, equals the negative 8. Whoa. And again, we end up with the x equals 7 and negative 9. Two ways to think about it. Again, really doing the same thing, same amount of steps. I guess I just recommend using the roots and powers just because it's probably a little bit simpler. Okay, number 8, part B, same idea. Pause the video, work through that one. Check your answer before we move on. All right, number 9, we're going to solve a radical equation where we'll say it's just a little bit uglier, a little bit more to deal with. The big thing with number 9 is notice there's an x inside the radical and on the outside. Okay, so we'll show you how to deal with that. Once again, the first thing we want to do is isolate the radical. So I'm going to subtract 5 on both sides of the equation. That'll leave me with a square root of x plus 7 on the left is equal to x minus 5 on the right. And then once again, what we'll do is we'll square both sides to cancel out the radical, to cancel out the root. Now the trick is on the right side, when I square a binomial, we've got to square the entire thing. So that's going to give us an x plus 7 on the left is equal to x minus 5 squared. Remember, that's the same thing as x minus 5 times x minus 5. So we actually have to distribute these out. We've got to FOIL things out on the right side. Okay, so for that, we'll go first. X times x will give me an x squared. All right, outer, x times negative 5 will give me a minus 5x. Inner will have another minus 5x. I suppose we could have combined those right off the bat. And then for the last, negative 5 times negative 5 will give me a plus 25. All right, so starting to look a little bit ugly, but once we simplify it, what we'll see is we're left with just a quadratic equation, okay, kind of thing we dealt with a bunch in the first semester. Really only thing I can combine here right off the bat is the negative 5x and the negative 5x. They'll give me a negative 10x. And remember, to solve a quadratic equation, we want to set things equal to 0. So I'm going to subtract x on both sides and the 7 on both sides, which leaves me with just a 0 on the left is equal to x squared minus 11x, and then plus a, let's see here, that'll be an 18. And then solving this guy, you can either use the quadratic formula or factor it. Up to you. I'm just going to factor this one. Let's see here, to get that x squared, I'll have just an x and an x. If I want something minus here, we'll have to, and positive at the end, we'll have to have two negatives. And then to get the 18 and the 11, what I'll need is a minus 9 and a minus 2. Okay, because negative 9 times negative 2 give me that positive 18. And then if I do my outer and inner piece, I'd have a negative 2x and a negative 9x that will add to the negative 11x there. Okay, so we know we did, in fact, FOIL things correctly. All right, once we have things factored, I can just set each of those factors equal to 0. I can say that x minus 9 equals 0 means that x is just equal to 9. And then also that when x minus 2 is equal to 0, that means that x is equal to 2 here. Okay, so two potential solutions. Now the last thing we're going to remind you how to do is how to check for extraneous solutions. Now where those are going to show up is when you switch from a radical equation to a quadratic equation. There might be solutions to this quadratic that weren't actually solutions to the original radical. Okay, so let's go ahead and test both those solutions. Let's start off with the 9. If I go square root of 9 plus 7 plus a 5, we want to see if that's equal to 9. So I suppose I could put like a question mark here. All right, 9 plus 7 is equal to a, wake up here, 16. So that'd be a square root of 16 plus 5. We want to know, is that equal to 9? Well, square root of 16 is a 4 plus 5 is in fact equal to 9. All right, so know that that solution does work. We'll do the same thing with the 2. So square root of 2 plus 7 plus 5. We want to see if that's equal to a 2. All right, 2 plus 7 is a 9, so square root 9 plus 5 equals 2. Not seeming promising here. 3 plus 5 is not equal to 2. Suppose we should have some question marks there. Okay, so that's how I know that that 2 is extraneous. The x equals 9 is the only good solution for this one here. All right, kind of a lot going on, but all steps you know how to do. We already looked at canceling out radicals, and then from there, again, you just have a quadratic equation to solve, and then testing solutions, okay, something we've been doing all through algebra. Okay, so put those things together. That's how we'd solve this one. All right, once again, give part B a shot. We'll run, pause the video, run through that one, check your answer. All right, last thing we're going to look at doing is graphing radical equations. And when I say radical equations, we'll look at the simple ones, just the square root equations. So we'll graph some square roots. We could also do third roots, fourth roots, fifth roots, etc. Okay, so if I want to sketch a graph of this guy, first thing I want to do is figure out what just a square root graph looks like. Okay, and for that, I'm going to make a table of, we could say, the parent function of x and y equals square root x values. Now, usually what we'll do is we'll plot some negative numbers. We'll plot 0, we'll plot 1, we'll plot 2. Let's kind of see what happens with this. Starting off negative, I can't take the square root of a negative number, so that's actually undefined. Let's throw some question marks. I'm not going to have a point at x equals negative 1. 0, the square root of 0 is just a 0. So our parent function here is going to have a point at 0, 0. Now I can also do the square root of 1, which is just a 1. So we'll also start off with a point at 1, 1. And then for 2, the square root of 2 isn't something nice. When I plug that into my calculator, I end up with a 1.4142 dot dot dot. In other words, I have a point I don't really feel like plotting here. Okay, same thing with the square root of 3. Okay, what I want to look for with the square root function is values I can find nice roots of. 4 is going to work. The square root of 4 is just a 2. So I'll also have a point at 4, 2. And then the last nice number that will fit on here that there is a nice root of is a 9. The square root of 9 is just a 3. Okay, so we'll throw a point at 9, 5, 6, 7, 8, 9, 3. All right, so that's my basic square root parent function. I suppose I can draw that better. I should probably hit all the dots. Oh, come on. There we go. And the next thing I want to do is look at making transformations on that function. The first thing we'll do is we'll take care of that times 2. Now if I take this function and multiply by 2, what that's going to do is essentially stretch it by a factor of 2. So we'll just take each of these points in red and double their y values. Now 0 times 2 is just a 0 still, so nothing changes there. 1 times 2 is a 2, 2 times 2 is a 4, and 3 times 2 is a 6. All right, so if we're keeping track of things here, in red, I have my just square root x. And in green, we have 2 square root x. And the last thing we'll do to finish this off is take care of the translations, the shifts up, down, left, right. Okay, just like with our other functions, when I subtract from the x, that's going to move things to the right. So this function is going to move everything, what was right here, right 1. And adding and subtracting to the outside moves it up and down. So here we'll have an up 3. So what I'll do is I'll just take each of these green points and move them right 1, up 1, 2, 3. Okay, right 1, up 1, 2, 3. Right 1, up 1, 2, 3. And then same thing, right 1, so kind of off the graph, up 3. Final graph is going to look like what we see here in blue. Okay, that's kind of the 3-step process for drawing this one. Now, if you're comfortable with it, there's some shortcuts you can take. You could shift to here first, then if you have that pattern in mind, you can just kind of create it with the stretch by a factor of 2. Okay, you could plot the stretch functions first, or if it really came down to it, what you could do is just go to this equation, okay, plug some values in and see what ones give you nice numbers, and plot what you see in blue right off the bat. Okay, so some different ways to work through it. We also want their domain and range. Okay, domain is the x values. Okay, the x values here run from 1 on up. So we'll say the domain is x is greater than or equal to 1. And then range is my y values. Well, the lowest y value is a 3. And then it continues up from there. So we'll say the y's are greater than or equal to 3. All right, and that is it then for our lesson on radical expressions, equations, graphs. Go ahead and before you move on, try part B, check your answer, make sure you're okay, good with that graphing stuff, and then from there you can move on to the Math Excel and start doing some practice on your own.